Let's build your concept step by step. First, we will discuss about different receptors of opioids. There are 3 families of endogenous opioid peptides released in the body in response to pain that are enkephalins, endorphins, and dynorphins. Endorphins are good analgesics. We now also know of endomorphins. This indicates that we have a natural system in the body that releases various opioid peptides in response to pain. These opioid peptides act on the opioid receptors mu, kappa, delta, and N/OFQ to relieve pain. Dynorphins are endogenous ligands for kappa receptors. Endomorphins are endogenous ligands for mu receptors with a high affinity. Endomorphin 1 and endomorphin 2 are known. Nosistin/orphanin FQ is another type of endogenous opioid peptide recently identified. It acts on the nosistin N/OFQ receptor, which is widely distributed in the CNS and periphery. All of the opioid receptors have been cloned. Subtypes have been suggested for each of them, viz. mu1, mu2, delta1, delta2, and kappa1, kappa2, and kappa3. Mu1 mediates analgesia, euphoria, and dependence, while mu2 receptors may be involved in respiratory depression and constipation. Here we will learn the opioid mode of action. Normally, a damage to tissue causes the release of chemicals, for example bradykinin, prostaglandins, adenosine triphosphate, ATP, protons that stimulate pain receptors and initiate firing in primary afferent fibers that synapse in lamina 1 and 2 of the dorsal horn of the spinal cord. The relay neurons in the dorsal horn transmit pain information to the sensory cortex via neurons in the thalamus. Morphine and other opioids produce their effects by acting on specific opioid receptors. These receptors are abundant in the CNS and other tissues. The opioid receptors are mu, kappa, and delta receptors. All opioid receptors are G-protein-coupled receptors. Stimulation of these receptors inhibits adenylate cyclase, resulting in decreased intracellular CAMP formation. They also facilitate the opening of potassium channels, leading to hyperpolarization. In addition to this, they inhibit the opening of calcium channels. All these result in a decrease in the intracellular calcium, which in turn decrease the release of neurotransmitters. Various neurotransmitters including dopamine, glutamate, GABA, 5-HT, and substance P are involved in the transmission of pain impulses. Opioids also directly inhibit the transmission in the dorsal horn ascending pathway. The pain threshold, primary sensory neurons respond to damage to the body by transmitting painful stimulus to the second-order neuron in the dorsal horn of the spinal cord. Then signals are further carried through the spinothalamic tract to the thalamus, and then to the somatosensory cortex where pain is perceived. Opioids also stimulate the descending pain control pathway from the midbrain and brainstem to the dorsal horn of the spinal cord. Opioid receptors are abundant in these areas, including the periaqueductal gray (PAG), area substantia gelatinosa, and the spinal cord. Next, here is an easy classification of opioid that includes agonist, mixed agonist-antagonist, and antagonist opioids. Let's learn the drugs included in this class. Agonists includes morphine, codeine, pethidine, methadone, oxycodone, oxymorphone, fentanyl, diphenoxylate, loperamide, dextropropoxyphene, tramadol, tapentadol. Mixed agonist-antagonists includes pentazocine, nalbuphine, butorphanol, buprenorphine, nalorphine. Lastly, antagonists. Antagonists that reverse the actions of opioids are also clinically important for use in cases of overdose. Naloxone, naltrexone, nalmefene, naloxegol. That's all for now. You can learn its details in next section, so stay tuned.